Hi guys, this is Sowjanya. Today I am going to discuss the topic about Quicksort. Through the whole video, we will be going through the following content. Quicksort introduction, its algorithm or logic, algorithm explanation with an example, and finally its time complexity. Firstly, let us look upon some introduction about Quicksort. This sorting technique was invented by Sir Charles Anthony Richard Hoare. We know that it is easier to sort a short list rather than a long list. As a short list contains only some elements, we can sort them out easily. But coming to the long list, it contains many elements and in turn it increases the number of comparisons, so it becomes somewhat difficult. So we will be thinking of a different technique, right? So the technique is divide and conquer technique. It's the concept of dividing the problem into small but similar subproblems is called divide and conquer technique. So Quicksort is based on this principle. Now in Quicksort, one element is considered as the pivot element and all the items which are less than or equal to the pivot element are placed in one sublist and all the items that are greater than the pivot element are put in the second sublist. The process involved in Quicksort is as follows. As we know that an array contains a list of n elements, so we'll be considering the first and foremost element of the list as the pivot element. Next step is to define two distinct variables, let them be as I and j. We will be assigning I to the start element and j to the end element of the list. And the next step is to increment the I up to the condition where a of I is greater than pivot, and we will be stopping there. Then the next step is to decrement j up to the condition where a of j is less than pivot and stop decrementing. If both incrementing and decrementing were stopped, we will be looking upon the next condition, that is, if I is less than j, then we need to exchange a of I with a of j. Repeat the above three steps from incrementation to the exchanging of element until when I is greater than j. If I is greater than j, finally we need to exchange the pivot element with the a of j element. Next, the quicksort logic. In this slide, we will be defining pivot, start element and end element. And here, if I is less than j, swapping of a of I and a of j will be taking place here. Here, if I is greater than j, we will be swapping a of j with the pivot element. And finally, repeating the above steps recursively from start to j minus 1 and j plus 1 to the end. Now let's have an example. First, let us consider an array of elements as follows. They are 50, 30, 80, 10, 40, 60, 20 and 70 from indexes 0 to 7. Here the pivot element is set at the index 0, that is 50, and the start is initialized at index 0 and the end is at index 7. Rules to be followed while sorting out elements. Compare A of start with A of pivot, and if A of start is less than or equal to A of pivot, then increment the I value, that is, move the position of the start to the next element. If A of start is greater than A of pivot, then stop incrementing I and keep the start at the previous place itself. Now compare A of n with A of pivot, and if A of n greater than A of pivot, then decrement the j value, that is, move the position of the n to one place less than that of n. If A of n is less than A of pivot, then stop decrementing j and keep the n at the previous position itself. Repeat the same process until when start is greater than or equal to n. Now the case is that if both the start and end are stopped, but if start is less than n, we need to swap A of start with A of n and then again continue the same process. If start is greater than n, then the swapping must be done to the elements A of n and A of pivot. Comparing A of start with A of pivot. Is 50 less than or equal to 50? Yes, it is true. So move the start to the index 1, that is to 30. Again comparing. Is 30 less than or equal to 50? Yes, it is true. So move start to the next index, that is 2. The element is 80. Again comparing. Is 80 less than or equal to 50? No, it is false. So start at the place itself, that is at 80 itself. Now the start is at index 2. Comparing A of n and A of pivot. Is 70 greater than 50? Yes, it is true. So move n to the index 6, that is to 20. Again comparing. Is 20 greater than 50? No, it is false. So stop n at the index 6 itself. As both start and end had stopped and start is less than n, we need to swap A of start with A of end. So by swapping, the array becomes like this: 50, 30, 20, 10, 40, 60, 80 and 70. Now start is at index 2 and end is at index 6. Next, moving towards left side and comparing A of start and A of pivot. Is 20 less than or equals to 50? Yes, it is true. So move start to the index 3, that is to 10. Again comparing. Is 10 less than or equals to 50? Yes, it is true. So move start to the index 4, that is to 40. Again comparing. Is 40 less than or equals to 50? Yes, it is true. So move start to the index 5, that is to element 60. Again comparing. Is 60 less than or equals to 50? No, it is false. So start at the index 5 itself. Now the start and end are at index 5. Next, moving towards right side and comparing A of end and A of pivot. Is 60 greater than 50? Yes, it is true. So move end to the index 4, that is to 40. Again comparing. Is 40 greater than 50? No, it is false. So stop end at the index 4 itself. Now the start is at index 5 and end is at index 4. Since start is greater than end, we should not swap A of start and A of end. Instead, we need to swap A of end and A of pivot. So on swapping A of end and A of pivot, the array becomes as follows: 40, 30, 20, 10, 50, 60, 80 and 70. Here, as we can see that all the elements to the left side of 50 or smaller and right side or greater. So the 50 is placed at its correct position. Repeat the same process as above to the left and right partitions, that is from indexes 0 to 3 and from 5 to 7. So finally, after applying the same process recursively, the elements become in the sorted order as follows: 10, 20, 30, 40, 50, 60, 70 and 80. Finally, time complexity of quicksort. In the worst case, it is of the order n square, and in the best and average cases, it is of the order n log n. Because for sorting an unsorted array with n number of elements, there is a need to make n into n minus 1 by 2 number of comparisons. In the worst case, now if the array is already in sorted order, then it requires only n number of comparisons. So the worst case, it is of order n square. In the best and average cases, it is of order n log n. Thank you.